All right, hello and welcome to your video lecture on this is 2.3, graphs that enlighten and graphs that deceive. So sort of ethical and non-ethical ways that we use pictorial representations of data in the world of statistics. Key concepts. We're going to introduce common graphs that foster understanding of data. We're going to discuss some graphs that are deceptive because they create impressions about data that are somehow misleading or wrong. And a lot of these graphs are provided to us using technology. So technology provides us with powerful tools for generating a wide variety of graphs very quickly and very easily. All right, so the first plot that we're going to look at is called a dot plot. By the way, this should be a short video. This is a short section. The sections will get more dense as we go. So dot plots are used when you have quantitative numerical data counts and measurements. So a group of quantitative data in which each data value is plotted as a point or dot above a horizontal scale of values. Dots representing equal values are stacked. So, all right, so the first thing I want to say is that just like with a histogram, you can tell the shape of this. And I would call this one, if I was going to say what the shape was, I would call this approximately normal, right? You can almost see this sort of standard normal curve, right in this data set, something like that. Maybe these are outliers. I'm concerned about that, right? Or wondering about that. Are these guys outliers, right? They seem to be outside of the normal value. I don't know, maybe these two over here as well. I'm not sure. But you can sort of see this sort of standard normal shape. And so one of the things that you can gain from creating a dot plot is that you get the shape just like you could with a histogram, right? So you could tell if it was uniformly distributed or normally distributed. I guess I just want to say, no, it doesn't want to let me get my eraser. I guess I want to say just normally distributed. Oh, there we go with everything. I'm using a different tablet because I had trouble with the other one. Right, so this is normal. Oh, it's doing the same thing. Lovely. Okay. I use a different, I have two plug and play tablets and I use the other one today because I didn't want to have this issue with the lines. I'm not sure what's going on. Must be my computer then. All right. And so how you read these is, well, each dot represents a data value. So if there are, and I don't know how many there would be, maybe there's 100 dots in this graph. Each dot represents a single data value. So this dot here is, it looks like it's just to the right of 40. So maybe this is 41, I don't know, or 40 and change, 40 and a half or something. And maybe this guy is 43. And then these two dots next to each other represent the same data value. So I have two 50s. So my data set could look something like this: 41, 43, 50, 50. And then notice that, let's call this 51. It's actually probably not. Let's see. So 52, 54, 56, 50. I guess it's 52. All right. So we have 52. Notice we have 1, 2, 3, 4, 5 dots. So that would be 52, 52, 52, 52, 52, right, is how it would look. And then we'd go on, right? The 6 dots here in this row, right? That would be, well, 54, 6 times. So each dot represents a data value. And this isn't something you would do by hand unless you had like a really small set of data. But it's useful because it does give us shape, right? We can identify potential outliers, that sort of thing. Okay, well, you get the point. All right, features of a dot plot displays the shape of the distribution of data. I just talked about that. And it's usually possible to recreate the original list of data values. So you can't with the histogram. I guess that's important to mention. So so notice here, I started to make a list of our data values, right? 41, 43, 50, 50, 52, 52, 52, 52, 54, right? So you can recreate the original data values. When you have a histogram, right? You have a histogram. Let's say it was the same data. Let's say your first class went from, let's call this 40.5 to, I don't know, 45.5. And then you had, let's say, I don't know, 7 in this class. Well, we don't know if they were all 41, or they were all 45, or right, one was 41, one was, we can't recreate the original list of data, right? All we know is that 7 data values fell between these 2 values, right? But we don't know what the original data values were. Here, you can see that we could recreate the original data set. So that's an advantage of using this particular plot, right? It gives you the shape and you can find the original data values, right? The histogram will give you the shape, but you can't recreate the original list of data values. All right, moving on. Stem and leaf plot, it represents, again, quantitative data by separating each value into 2 parts, the stem, such as the leftmost digit, and the leaf, such as the rightmost digit. All right, so right here, right, this first row here, this is 2 data values. It's 40 and 42, right? So the number on the left gives you the first digit, and the number on the right gives you the second digit. And this is 2 data values. So the stem is on the left, the leaves are on the right, and each leaf, each number that we see on the right is a data value. So in this first row where 4 is the leaf, we have 2 data values. In the second row where 5 is the stem, right, we have all of these leaves. Each of these leaves represents a data value. So this would be 50, 50, 52, 52, 50. Oh, this is the same. This is the same data, I believe. 50, 50, 52, 52, 52, 52, 52, 54, 54, 54, 54, 54, 50, right, etc. At the bottom here, when we get to the end, right, these are, well, that's 102 and 104 are the last data values. So each of the numbers, each of the leaves over on the right represent a data value. And you can get a sense of the shape here. It's turned on its side a little bit, but you could still sort of tell, like I can tell, right, here's the shape of this thing. I know, it's kind of weird to see it this way, but you can tell that it's normal. Most of the data is centered here in the middle, right? That's how we know it's normal, when most of the data is in the middle and less data is on the sides. So even though this one is, I guess let's call it horizontal instead of vertical, you can still get a sense of the shape, right? And this one I would call normally distributed, right? It's symmetric and bell-shaped in some sense. All right, so it shows the shape of the distribution and it retains the original data values. And the sample data are sorted, arranged in order. Okay, well, I guess that's also true. They didn't mention it here. These are also in order. But you can recreate the original data. In fact, that's the whole point of this, right? Is that you could very easily recreate the data. So 40, 42, 50, 50, 52, 52, right, et cetera, all the way up to the last 2, which are 102 and 104. So it's another data set that allows you to recreate your original data if you weren't given the data set. All right, a time series graph, right? It's used for quantitative data again. That's been collected at different points in time, such as monthly or yearly. So a lot of times we'll look at the stock market or housing prices or different things with a time series graph. And it shows you how, in this case, law enforcement fatalities have changed over the years. So 2001 looks like it was a really bad year. There were 240 law enforcement fatalities. And then whatever this is, let's call this 2017 or something was a really low year, right? We didn't have very many at all. And so we can see over time how the data is changing. So it reveals information about trends over time, right? So do we have our fatalities increasing? Are they decreasing? Are they kind of staying the same? I would say here, I think overall it looks like a decreasing trend, right? But I would say only slightly so. But the trend does appear to be decreasing here. If we were to exclude this one year where it's really high, right, this guy right here, I would say that the trend is overall down. All right, bar graphs. So this is for categorical now, qualitative data. So it's like a histogram, but the bars don't touch each other. So a graph of bars of equal width show frequencies of categories of categorical or qualitative data. The bars may or may not be separated by small gaps. Okay. Yeah. Okay. I guess they contradicted what I said. To me, a bar graph is separated. They're saying that it doesn't necessarily have to be. So it shows the relative distribution of categorical data. So it's easier to compare the different categories. Are they going to show us one? No. I don't know. It would be, it would be, these would be frequencies. And so over here, we would have something that's qualitative. So maybe your year in school. Oh my gosh. Wow. And so maybe we have freshmen, and then maybe we have sophomores. Lovely. And then we have juniors, and then we have seniors. So it would look something like this, right? So it shows the frequencies for qualitative data instead of quantitative. And a lot of times they have a code, right? Maybe this is a blue, and they over here they say blue is freshman, right? They have a lot of features like this. All right. Pareto charts. A Pareto chart is a graph for categorical data with the added stipulation that the bars are arranged in descending order to frequency so that the bars decrease in height from left to right, right? So just like the bar graph, but in descending height. So if we had the most amount of sophomores, and then we had seniors, and then we had freshmen, and then juniors, right? Something like that, right? So I can't remember what I said. I think I said sophomore, junior, senior, freshman, something like that, right? So the bars would be in descending order, right? Frequencies high to low. All right, so it shows the relative distribution of categorical data, so it's much easier to compare different categories, and it draws attention to the more important categories, right? So you notice what there is the most of, right? So let's say it was political parties, and this was the highest, right? You would know that there's the most of whatever this is, Democrat, Republican, Independent, I don't know. Right, it draws attention right here to the largest bar. Oh, and here's one. So Pareto chart of stolen boats. So jet skis are the highest with almost 1,400, and then motorboats, utility fishing, right, sailboats, etc. Right, so it calls attention right away. We know that jet skis are stolen much more than the other types of boats. All right, pie charts, right? You've seen them lots and lots of times. A very common graph that depicts categorical data, right? So notice that the last 3 or 4 have been all categorical. Just the first 2 were quantitative, the dot plot and the 7-leaf. So a very common graph that depicts categorical data as slices of a circle in which the size of each slice is proportional to the frequency count for the category. Are they going to show us one? Shows the distribution of categorical data in a commonly used format. There we go. All right, so this is the same data, right, that we saw here. And jet ski should have the biggest piece of the pie, right? You can calculate that area. It's going to be the largest area, right? So here's the jet ski, right? This big blue area, right? And we can see sailboat has a much smaller area of this circle, right? So just looking at it, we know jet skis are stolen the most, followed by motorboats, right? Et cetera, et cetera. And you've seen these lots of times. All right, frequency polygon. All right, it's a graph that uses line segments connected to points located directly above class midpoints, right? Those are the values that come from your frequency distribution, right? We talked about those a lot, right? So those are the class midpoints. A frequency polygon is very similar to a histogram, but the frequency polygon uses line segments instead of bars. Hopefully they have one. A variation of the basic frequency polygon is the relative frequency polygon, which uses relative frequencies on the vertical scale. Are they going to show us? Okay. So this one is a frequency polygon of McDonald's. This is the McDonald's data again. And so instead of having a bar here, they're going to have, right? So instead of having a bar sort of here, and one here, kind of move this. And one here. And one here, one here, and one here, right? So instead of shaping it like a histogram, right, this dot here represents the midpoint for the class, right? The midpoint for each class. And so it can show you the same sort of information that the histogram does. I'm looking for my erase. All right, so we know that about 12 of the times were around 99.5 seconds. Doesn't mean that that 12 were exactly 99.5. That's the midpoint. So 12 of them were around that time, and 24 were around 149.5 seconds. And it looks like 10 of them were around 199.5. So it doesn't mean, let's be careful because it's the midpoint. So it doesn't mean that there were 9 that were 199.5 seconds. It means that there were 9 or 10, whatever this number is, that were around there, that were close to that. All right. And then you can compare, right? So we did this before with I think we used, I think they were frequency distributions. They weren't histograms, but we looked at the Dunkin' Donuts compared to McDonald's. And this is just another way we could see that Dunkin' Donuts tends to be faster at the drive-through than McDonald's. Okay. Now, these aren't relative yet. Oh, they are. Okay. So this one is a frequency polygon, right? So notice on the vertical axis, we have frequencies 5, 10, 15, 20, right? So we can say for this largest class here, 149.5, about 24 of the data values were around here. But the next one is the relative frequency. So it gives you the percentage. So if we're talking about the same data value up here, well, it's almost 50% of the times were around 149.5. So not the number of, but the percent of, right? So the relative frequency polygon gives you the percents, and the shape will be the same, right? The shape will be, look, it's exactly the same. Just the way we label it is different. All right. And so the next thing we're going to talk about is that statisticians aren't always ethical, and there are some things that we can do to deceive the public. So a common deceptive graph involves using a non-vertical scale that starts at some value greater than 0 to exaggerate differences between groups. All right, so this is a really good example of this. So on the left is the deceptive graph. On the right is the accurate graph. So it says always examine the graph carefully to see whether a vertical axis begins at some point other than 0 to see that the differences are exaggerated. So notice here we're starting at 0, right? Here we're starting at 10%. So they've sort of cut off, and 10 is up here, right? So they've cut off this bottom, right? They cut off the bottom to make it appear, right, that OxyContin, for whatever reason, is, I don't know if it's more effective. What is it we're talking about? Oh, yeah. So this is the percentage of people experiencing nausea. So they're trying to make it look like, why would it be more? I don't know. I guess maybe this is a case against OxyContin. So they're saying that there's a huge jump from placebo to the people experiencing nausea on OxyContin. I guess I'm going to try to stop reading too much into it, but the point is that they've, for whatever reason, right, they've made a point to be deceptive about the way that they're showing this. When we look at the actual percentages next to each other, we can tell, well, it's maybe about twice as much, but it's not clear here, right? If you're not careful about reading the percentages on the side, it just looks like OxyContin is, 10 times higher, right, for nausea than placebo. But if you look at the graph to the right, you can see that that's not the case. It's about twice as high. All right, drawings of objects called pictographs are often misleading. Data are one-dimensional in nature, such as budget amounts, and then depicted as two-dimensional objects, such as dollar bills, or three-dimensional objects, such as stacks of coins, homes, or barrels. Okay, that's another way that we can be deceptive. By using pictographs, artists can create false impressions by grossly distorting differences between or grossly distort differences by using these simple principles of basic geometry. When you double each side of a square, its area doesn't merely double, it increases by a factor of 4. And when you double each side of a cube, its volume doesn't merely double, it increases by a factor of 8. Okay, so here we go. In 1970, 37% of US adults smoked. 2013, 18% of US smokes. So they are distorting this multi-dimensional object in a way that it makes it look like the difference is greater than it is, right? We're talking about, what is that, like a less than 20% difference, or it was 21? No, 19% difference, and they're making it look like it's much greater, right? So they're using principles of area to sort of deceive and make it look like the amount has decreased a lot more than it has. All right, you guys, that's what I have for you. So happy studying. I will see you on the next video. I guess I should talk about this. All right, so it says concluding thoughts. In addition to the graphs we have discussed in this section, there are many other useful graphs, some of which have not yet been created. The world needs more people who can create original graphs that enlighten us about the nature of data. In the visual display of quantitative information, Edward Tufte, I don't know who he is, offers these principles. For small data sets of 20 or fewer, use a table instead of a graph, right? So a frequency distribution would work. A graph of data should make us focus on the true nature of the data, but not other elements such as eye-catching but distracting design features. Do not distort data. Construct a graph to reveal the true nature of the data. And almost all of the ink in the graph should be used for the data, not for other design elements. So there shouldn't be distracting items in your graph. Be as straightforward as you can is the takeaway. All right, now I'm done. I will see you on the next video.